Hello, everyone. Today is our great pleasure to have Professor Dmitry Swazdyarsky from University of Washington to give us the seminar talk. So, Professor Swazdyarsky received his PhD from the Operation Research and the Information Engineering Department at Cornell University. And after that, he did, I think, 1 year postdoc at the University of Waterloo. And after that, he joined the Department of Mathematics at the University of Washington as an assistant professor. So he got several awards, including the Air Force Young Investigator Program Award and NSF Career Award, and also the Young Researcher Prize in the Informs Optimization Society, and the finalist of the Tucker's Prize, and also Young Researcher Best Paper Prize. So today he's going to talk about a non-smooth optimization, about the active strict saddles. Welcome.
Thanks a lot for the introduction and for the invitation. It's a pleasure to be here virtually. Okay, so I'll talk about exactly what Yang said, so avoiding saddle points and non-smooth optimization. This is joint work with Dave McDavis and Liwei Zhang, who's they're both in Cornell. Liwei is a student of Damic. And primarily, about, I don't know, maybe 90% of the talk will be an earlier paper that I wrote with Damic a year and a half ago, but it's necessary sort of to understand the more recent work. Okay, so what's the basic question we want to understand? Well, there's a phenomena for smooth optimization, which essentially says that, well, there's a philosophy which essentially says that saddle points are really not a problem for minimizing smooth functions, in the sense that really if you have a C2 smooth function and you have extraneous saddle points, these are critical points that are not locally optimizing, not locally minimizing, then they're rarely encountered by algorithms. Okay, and so essentially, in a sentence, what this means is that simple algorithms for minimizing C2 smooth functions will avoid all strict saddle points when randomly initialized. So all points, roughly speaking, that are not local minima will be bypassed. And this is kind of the cartoon picture of it. So this is a critical point like here. So in one direction, the function is increasing, in the other one's decreasing. But typically what will happen if you apply an algorithm like gradient descent, what will happen is that algorithms will basically bypass. They will kind of move very, very close to the critical point, never hit it, and just move along away from it. Okay, and this is kind of a basic realization that's been that has taken hold in optimization. And so what simple algorithms means, the mean are gradient descent, coordinate descent, and various other algorithms of a similar flavor. And so precisely what is meant by strict saddle points, these points that you want to avoid, those are just critical points that admit negative curvature. So the minimal eigenvalue of the Hessian is strictly negative at these critical points. So these points one would expect should be avoided by algorithms. And the reason why this is interesting is that you can justify that for a variety of estimation and learning problems, all of these critical points that you do not want to be attracted to do turn out to be strict saddles and are therefore avoided by numerical methods, and they're really not a problem. Okay, so the main question, so just to sort of summarize in concrete examples, local minimizers are good. Extraneous critical points are such that there's negative curvature around them, and therefore, in a very strong theoretical sense, randomly initialized first-order algorithms will avoid them. Okay, so the basic question we want that we sort of set out to understand is to what extent is an analog of this statement true for non-smooth functions. So, and the very basic question one can ask is the following: if I give you a more or less generic non-smooth optimization problem, is it true that simple algorithms converge only to local minimizers and not to extraneous critical points? That's the question. Please feel free to interrupt me at any time. It would be nice to have, with these kind of online things, it's nice to have more of a discussion than a lecture. Okay, so in order to understand this question, to answer this question, it's very hard to think about just generic non-smooth optimization problems because generic non-smooth problems are extremely pathological. So it's convenient to introduce a broad problem class of non-smooth functions that are still amenable to analysis. Okay, and so the kind of assumption that we're going to work with, and this is something that Damik and I have been working on for a few years now, is this notion of weak convexity. So we'll primarily be interested in problems that are weakly convex. What this means is the following: we're going to be interested in minimizing a function so that the function f itself may not be convex, but if you add a big enough quadratic to it, it does become convex. That's our assumption. So a function is called rho weakly convex. If you add to it rho over 2 times the quadratic, it becomes convex. And there is a large class of examples that's good to keep in mind. So the main examples in my mind of these sorts of problems are compositions of convex functions with smooth functions. So convex functions by themselves, okay, so you have a convex function, you have a smooth function. If you compose them, the answer is neither smooth nor convex, but it is weakly convex. Okay, so if you compose a convex function with a smooth function, it is weakly convex. So we can understand these sorts of examples under the umbrella of weak convexity. Another important class of weakly convex problems comes from pointwise maxima of smooth functions. That's another kind of interesting example. Okay, very good. So this is going to be our problem class. And I want to sort of just illustrate why one would care about weakly convex minimization. Why would one care about such problems by an example? And then after an example, I'll discuss this question of, well, okay, do simple algorithms converge only to local minimizers? Or can they get stuck at extraneous critical points? Okay, so just as an illustration, I want to look at a class of problems that correspond to low-rank matrix estimation. So a prototypical class of problems in signal processing and statistical learning is as follows. Given a certain rank R matrix, M sharp, so this is the ground truth, let's say it's positive semi-definite, symmetric, and R is much smaller than D, which is the dimension of the matrix. What we get to observe are measurements of the matrix M sharp. Okay, so we get to observe the trace product of M sharp with certain matrices A sub I, and we get to see BI. The goal is to recover this low rank matrix M sharp from the BIs and AIs. Okay, so there is a wealth of problems that fall into this category, such as matrix completion, robust principal component analysis, phase retrieval, by linear sensing, what have you. And there's a natural non-convex penalty formulation. Okay, so a very natural non-convex penalty formulation simply collects all of these A sub i's into a single linear map. So A of M just records these dot products with M, not with M sharp, but with M as a vector, and subtracts off the observations and takes some kind of residual norm. And the idea is then, okay, you want to minimize this residual error over all matrices that have small rank R. The typical way okay, so this is a rank R. So this constraint is not so good. It's a highly non-convex constraint, a very typical non-convex and non-smooth constraint. And so the typical way to reformulate that is by this Buer-Monteiro factorization, introduce a nonlinear representation of rank R matrices by a factored matrix XX transpose, where X is now D by R. So all of these matrices are at most of rank R. And so now here's the problem we're going to be interested in for recovering M sharp. We're going to be optimizing over D by R matrices of some norm of AXX transpose minus B. Okay, so this is our smooth function. and the norm is our non-smooth outer function. So these problems are weakly convex. And these sorts of problem formulations arise from a variety of contexts. So why would you want to minimize, let's say, some norm? Like, which norm should you use? Well, the norm is actually the best norm to use depends on where the a sub i's come from. So, for example, the typical norms that one would want to use in order with theoretical basis is the L2 norm or the L1 norm. So using the L2 norm is from the viewpoint of non-smooth optimization is not very interesting because if you square it, becomes smooth. However, in many important cases, the L2 norm is inappropriate for recovering the matrix M sharp using an optimal number of measurements. What you want to use is a scaled L1 norm, which is inherently non-smooth. Okay, and the reason is that the L2 norm is only useful under basically L2, L2R restricted isometry properties. Well, typically, which corresponds to, which happens, for example, if the matrices A sub I are Gaussian, and that leads to smooth problems. But there are many cases where these matrices A sub I are not Gaussian, they're structured, maybe there are certain random rank 1 matrices, such as in phase retrieval. In that case, it turns out the more appropriate norm to use is the L1 because it allows restricted isometry properties to kick in different norms. In that case, you cannot get away, in some sense, from using this kind of non-smooth penalty if you want to sort of optimize directly the kind of the norm that comes from restricted isometries, isometry properties. Okay, in any case, this is a motivation for thinking about problems that are weakly convex. Because here's an example, a norm composed with a smooth map. Okay, so good. So we have our problem class. We have a problem class of weakly convex for weakly convex minimization. We would like to understand now, again, returning to the basic question: do basic algorithms on weakly convex problems avoid extraneous critical points? That's the question. Well, okay, so the next step, so we have the problem class. The next step I need to explain to you is, well, what algorithms are we talking about? So that's what I'll do now. And then after that, I'll try to explain, well, what are extraneous critical points? How does one understand critical points in this more general non-smooth setting? Okay, good. So, okay, so what algorithms should we talk about? Well, I'm going to focus on a few different algorithms. So they can all be understood as a single kind of iterative process based on model approximation. So the sorts of algorithms I'll be thinking about simply proceed as follows. So I'm trying to minimize, so let me just go back to this. Okay, we're minimizing a function f. I'm going to just think about a class of algorithms, and we'll look at a few examples, where in every iteration, what I do is I form a certain model, a strongly convex model of my function with base point xt. So xt is going to be forming the model. I'm going to minimize that over the y. The minimum of that is the minimizer of that is going to be my next iterate. Okay, so let's look at some concrete examples. So the proximal point method proceeds as follows. So if I want to minimize a function f, what I would do, my model would be to add to take my function, add a quadratic penalty from xt and minimize that, and that would give us xt plus 1. If my function is a composition, again, the most important example, composition of a convex function with a smooth map, a reasonable model comes from what is called the prox-linear method. So what it would do is, given a certain iterate xt, it would linearize the smooth map. Okay, so we have an inner smooth map. We'll just linearize it at xt, and we add a bit of a quadratic penalty relative to current xt. And then we're going to minimize this model over y. So this is kind of a Gauss-Newton type of procedure. Okay, this is yet another algorithm. Okay, so and there are various other algorithms in the same family. Okay, so I'm just for example, the proximal gradient method can be understood as an example of the prox-linear procedure, where you have a smooth function plus a non-smooth function. So in every iteration, what you do is that you linearize the smooth part, add a bit of a quadratic, and minimize that, and that's going to be your next step. Okay. Okay, and so So these are all the algorithms we're going to be able to talk about, okay? These three: prox point, prox linear, prox gradient. So those are the three algorithms to keep in mind. Okay, so we have two ingredients. What is a non-smooth problem we're going to be thinking about? The ones that are weakly convex. What are the algorithms we're going to be thinking about? Well, these basically: proximal point, prox linear, prox gradient. These simple processes. And then the final thing is I need to understand. Well, okay. So now let's talk about what are the saddle points I may expect to avoid. Okay. So let's go back again to the smooth setting. So in the smooth setting, I was a bit vague about this, but it is not exactly true that you can avoid any saddle point, any extraneous critical point. You can avoid ones that have negative curvature. So a strict saddle for smooth optimization, if your function is C2 smooth, is any point that's critical and has negative curvature. These are the points that are avoided by gradient descent, for example, if you start almost anywhere. They will not be attractors of gradient descent. Okay, so the key idea now is we need to understand what is the analog of such a property, of such critical points, for non-smooth optimization. And there are two challenges here. The first challenge is that whatever definition we make needs to allow us to deduce that these are the points that are avoided by reasonable algorithms, like on the previous slide. But on the other hand, we need to show that this is a reasonable property, whatever property we come up with. We need to show that more or less for generic functions, they should really only have these kind of strict saddles, these avoidable saddles. Okay, so it needs to be on one hand narrow enough to be able to prove something about them. On the other hand, general enough to actually hold for typical problems. Okay, so and this is kind of where the interesting part it gets started. So we want to understand again some notion of extraneous critical points that are avoided by algorithms. Well, maybe the first step is to try to rewrite this property without ever mentioning gradients or second derivatives, and this is easy to do. All that this property tells us about the minimal eigenvalue Hessian is that there is directions of second order descent. Okay, so the property I just highlighted simply means that there exists a certain direction v, so that if you move in that direction, the function gap, the amount by which you decrease is on the order of a square, t squared. Okay, for every small t. So there are directions of second order decrease. This has nothing to do with smoothness. This is a purely metric condition. So you can ask, okay, what if we look at critical points for which this is true? There exist directions of escape that are second order. Does that suffice for are these saddle points avoidable? Are these critical points avoidable for non-smooth optimization? And the answer is actually no. Right. So negative curvature is actually not enough outside of the C2 smooth setting. So here's an interesting example. So this is a C1 smooth function. So it looks like a downward quadratic along this axis, and it looks and it's going up along the other axis. So there are definitely directions of negative curvature. So this is an extraneous critical point. It is not locally minimizing. In one direction along one axis, it's going up like a quadratic. In the other direction, it's going down like a quadratic. So in particular, there are directions of negative curvature. But actually, if you look at basic algorithms like gradient descent on this problem, there are initial conditions that are actually attracted to this critical point. And one way to see that is to look at the situation in continuous time by looking at the gradient flow. Okay, so if you look at the gradient flow, if you start anywhere within this kind of cone of initial conditions, they're attracted to the origin. Okay? Outside, they're repellent, so the origin is repellent. But there's a whole cone around of initial conditions. So if you start there, the flow actually traps you, attracts you to the flow moves the iterates to to the critical point. So curvature by itself, even for C1 smooth functions, is not enough. Negative curvature is not enough to ensure that basic algorithms escape. And kind of maybe the intuitive reason why is that the flow does not reach, so like the flow within this cone of initial conditions, it does not reach the axis quick enough to benefit from the negative curvature. Okay. And so I'll make that precise in a little bit. Okay, and so there's an extra ingredient that's missing. So if we want to understand what are the critical points that are avoided by first order, by simple algorithms, curvature is not enough. We need an extra ingredient. There's something missing. And the thing that's missing is the following condition. So let's look at let's contrast, so sort of ignore the text. Let's just look at the picture. Here's a contrasting picture of a saddle point, of a critical point that is avoidable. Okay, so here's a function. It's smooth along this axis and has negative curvature, and it's not smooth in the opposite kind of directions. So it is an extraneous critical point. It is not locally minimizing, but it has directions of negative curvature. Let's look at the gradient flow. The gradient flow, if you look at it, you see that the set of initial conditions that are attracted to the origin has zero measure. It's only along this axis. Oh, sorry, it's only along this axis, excuse me. If you start outside of this axis, where my mouse is, you always get repelled from the origin. So this is somehow the opposite of the previous picture. In this picture, the saddle point, this critical point is avoidable. In the previous picture, this critical point was not avoidable. Both were, despite having negative curvature. Okay, so what is different in this new picture, in this better picture, is the following. If you look outside of the axis along which there is negative curvature, the gradients are all bounded away from zero. So this function looks very sharp in normal directions to the axis of smoothness. That's what this says. So f grows sharply away from the axis of smoothness, in the sense that the infimum of the norm of the gradient is bounded away from zero. Okay, it's kind of V-shaped. Okay, and this is exactly the condition that is missing. Okay, so here's the key definition of what we will mean by an active.
There's a question here.
Yes.
It looks like your two examples, like the gradient flow, the picture, I didn't see the difference. So like this slide, you say it will expel from the origin.
Yeah, so if you look, maybe it's sort of hard to see, but if you, so you see my mouse, right? So if you start within this region, like for example, if you flow,
right?
So all these initial conditions are attracted to the origin, right? So everywhere here within this cone,
So,
all those
for
points
the example, if you approach to that, the horizontal axis, the x-axis, it would expel from the up or the bottom, that blue region.
You do if you start here.
Right, right.
If you start here, you get attracted.
Oh, I see. Okay, I see the little arrow toward to that axis.
Yeah, they're all pointing toward. So there's a transition that happens along this kind of diagonal, basically. There's a transition here. So once you get past, so there's this cone, you see.
I see.
Okay, so within this cone, if you start, you end up at the origin. If you're outside this cone, sort of on the bottom of it, then you'll get repelled. But the main point is that this cone has positive measure.
Right,
and in fact, you can make a high dimensional picture where this is a huge set.
Right. Okay, thanks.
Yeah, sure. Thanks for the question. And here the opposite happens. Everywhere you start except for the x-axis, everywhere else you get repelled. And that's what you want. So the only attractors, the initial conditions that get attracted to origin is the x-axis, which has zero measure. So those are the bad initial conditions. Great. Thank you. Okay. Good. Okay. So this is what we have to make sense of. Okay, we need to make sense of this extra condition that did not exist for smooth optimization. For smooth optimization, curvature determined everything. For non-smooth optimization, it is not just the curvature; it is something else. Okay, and so what is the definition that we're gonna need? So we're gonna need the definition of activity, and this is a very old idea in non-smooth optimization. So I have some references. This idea is very old, so I'll use one definition of what we will mean by an active manifold. So one definition of an active manifold. So this active manifold is just going to generalize what we mean by the axis here. So you see the axis is interesting because the function varies smoothly along the axis and sharply in orthogonal direction. Okay. So the fact that the axis was linear is not going to be important. The fact that it's a smooth manifold will be important. And so here's our definition generalizes this axis in this example. So we will say that a critical point lies. So we'll say that a critical point lies on a C2 smooth active manifold M. Again, M is the analog of the axis. If F varies smoothly along M, so that means that if you restrict F to M, it's smooth. So just like in the picture. Okay, so this function is not smooth, but if you restrict F to the axis, it's a simple quadratic, so therefore it's smooth. And the second key ingredient is the sharpness condition, which tells you that if you look outside of M, and you look at all gradients, or more generally subgradients, let's ignore that distinction for the moment, they're all bounded in norm away from zero. So just like in this picture. Okay, all gradients, or more generally subgradients, have to be bounded away from zero outside of this manifold M locally. Okay. Good. So this is going to be this key structural this key object that we're going to assume exists. So here's just a kind of a curvy example. So again, here's a function. The active manifold here is this parabola. So why is it active? Well, because if you restrict the function to the parabola, it's actually zero. So that's pretty smooth. And outside of the parabola, the gradients are all bounded away from zero in norm. Okay. So the advantage of working with nonlinear objects, it allows you to look at these nonlinear manifolds. Okay. Good. Okay, so this is this key definition. So this is the second ingredient that was missing. So we need an existence of this active smooth substructure, active manifold, and then once we have this active smooth substructure, once we assume it exists around the critical point, it's straightforward to understand what we can mean by negative curvature. So here's the key definition. We'll say the critical point is an active strict saddle. These are the critical points we expect to be avoided by simple algorithms. If F admits an active manifold M containing X bar, so just like in the picture, like that curvy object, there should be, if I'm looking at the critical point, there should be some active smooth manifold, so that the restriction of the function to the manifold should have negative curvature in some directions. And formally, the way you say that is that there should exist some curve inside this smooth manifold, which starts at x bar, and so that if you look at how the function f evolves along the curve, it has negative second derivative, which just means that it decays quadratically quickly along this curve. Okay, so that's it. That's the definition. This is the key definition. So this is what we mean. This is the analog of a strict active saddle. There are two ingredients: existence of an active manifold and negative curvature along the manifold. Okay. So this definition would not be interesting if it didn't hold in practice, right? So you would really want it to hold for a wide class of examples. And one would need to justify that this definition is reasonable. So one way to justify it is through the following theorem. Right, so one way to justify it would be to look at concrete examples. But a very different way of thinking about it is very classical in mathematics, is that you ask, if I take a function f, for which maybe it has critical points that are bad, that are not, in a sense, active strict saddles, right? Like for example, if I take this function, like this function does not have this property. If you look at the origin, it is not an active strict saddle because it does not admit this active manifold. Okay. However, you can ask, okay, is this a typical property? What if I slightly tilt this function? Would all the resulting critical points then be strict saddles? Okay, and the answer is yes. So this is this theorem, which justifies why this is a reasonable definition. If I take a reasonable function f, so I take a base function f, which is semi-algebraic, which just means that its epigraph is cut out by finitely many polynomial inequalities. Anything you want sees in practice in optimization, essentially, is semi-algebraic. So if I have to take a semi-algebraic function and it's weakly convex, and I now take so that function f might have critical points that are not active strict saddles. However, let's look at what happens if I take a perturbation of this function. So I take a full measure set of perturbations v, and I replace my function f by linear tilt. So this is just saying, okay, I slightly tilt my function, slightly perturb it. What happens now? Well, you can show that if you slightly perturb your function by almost any perturbation in the sense of the Lebesgue measure, then any critical point of this function is either a local minimizer or an active strict saddle. So in this way, this is a very reasonable property because, okay, it might not hold in a concrete example, but if you slightly perturb your example, it would hold at every critical point. Okay, so this is just the justification for why this is a very reasonable property to look at. Okay, so again, returning to this example, this critical point is what this theorem says. This is a highly unstable situation. This critical point disappears as soon as we slightly tilt the function. You slightly tilt the function, the origin is no longer the critical point, and around every other critical point, you would have the right kind of behavior. Okay. Good. Okay, so good. So we have the three ingredients. We have the problem class, we have the algorithms, and we have a definition of what we believe are avoidable saddle points, avoidable critical points. And we also know this is a somewhat reasonable property, being an active strict saddle, because it's generic in the sense that I just described. Okay, so the last thing we need to argue is that indeed these points are avoided by basic algorithms, by the three algorithms I wrote down in the beginning. So you remember, our algorithms all have the same shape. At every iteration, they form a model, some kind of strongly convex model, local model of your function. You minimize that, and that becomes xt plus 1. Okay, so the way that we're going to prove, the way we're going to understand, well, okay, do these processes, when initialized almost anywhere, do they avoid active strict saddles? Is we're going to think of this algorithm as just a fixed point iteration. So we can think of this process as just a fixed point iteration for well-behaved operator t, and the operator t is just defining the algorithm. Okay? And the critical points are precisely the fixed points of this operator that defines the algorithm. And now when we're going to look at this operator, so now in generally speaking, this update map that goes from xt to xt plus 1, this fixed point map, is not going to be smooth because your problem is not smooth. However, we will see that for the three algorithms, as soon as we have a active manifold, they are smooth locally around the active manifolds. They're not globally smooth, but they will be smooth around the active manifolds. And once we make this realization, we can try to sort of use smooth techniques to understand the fixed point iterations. And the smooth techniques boil down to what's called the stable manifold theorem. That's used in a smooth setting. So this is kind of the high level idea, is that we write down our algorithms as fixed point iterations. They're not globally smooth because the problem is non-smooth. However, as soon as we know that around the critical point there is an active manifold, one can prove that these update maps become locally smooth. And once they become locally smooth, we can use smooth techniques to understand them. Okay, so let's sort of go through this kind of exercise for the simplest possible case for smooth functions. Okay, just to sort of be clear what are the key ingredients to make this work. Okay, so let's look at, so again, we're looking at the fixed point iteration. Our goal is to understand when this fixed point iteration avoids some fixed points. Okay. So for example, for gradient descent, for smooth optimization, the fixed point iteration is just this: identity minus the step size times the gradient. Okay. And so the recipe for smooth functions is as follows. Once you, if I look at a strict saddle in a conventional, typical sense for smooth optimization, that just means gradient is 0 and the minimum eigenvalue of the Hessian is negative. That immediately implies that the Jacobian of the corresponding gradient descent update map has an eigenvalue of magnitude strictly bigger than 1. And so in the sense of, if you sort of go back to dynamics, this means it's an unstable fixed point. And there is a classical center stable manifold theorem, which immediately implies that the set of initial conditions has Lebesgue measure 0. So in other words, as long as the Jacobian has an eigenvalue whose magnitude is bigger than 1, there is the standard theorem which tells you that the set of initial conditions that are attracted to that fixed point has measure 0. Okay, this is the basic process you go through, proof outline for smooth optimization. How do you argue that gradient descent avoids strict saddles? Okay. And so as a result, the random initialization does not land in this 0 Lebesgue measure set, and the algorithm avoids saddle points if you start almost anywhere. Okay. So there's basically, so those are the ingredients. Okay. You need to translate strict saddleness into some properties of the Jacobian of the update map. Okay. And so
Can
that's
I
exactly
clarify something?
Yes, please.
So here you say it's unstable. So that means the iteration may diverge, right?
Yes. So basically, so there's a definition. So something is you say that a fixed point of a map T is unstable if this holds. This is a kind of
Right.
this is the definition. So it's unstable if it has an eigenvalue of magnitude strictly bigger than 1.
Right. So I mean, if you start in, say, from some random points
Mhm.
and apply this fixed point iteration, it may diverge, or it converge, but it will not converge to the strict saddle, or with
Right.
measure 0.
So the goal is to say the following. The goal is to say that the initial conditions from which it will converge to a strict saddle has 0 measure.
Right.
Right, because the goal is to say that we don't converge to them.
Mm-hmm.
So if this is what it's saying, that if you have an unstable fixed point, then the set of initial conditions from which the fixed point iteration will converge has 0 measure. So if you start randomly, you will not fall into the set, roughly speaking.
I see.
Okay. Good. Okay. So like I said, so this is the general recipe just for gradient descent. How you argue in this very classical settings, you need to translate strict saddleness property into, this is a property of the function, into, right, it's a property of the function. You need to translate that into a statement about the Jacobian of the update map. This is a property of the algorithm. Once you know that the Jacobian has an eigenvalue of magnitude bigger than 1, there's a standard theorem you apply, center stable manifold, and you're done. This is the outline of the argument for smooth problems. Okay, so let's play the same game, or try to play the same game. Okay, so we have the update map. So this is the update map corresponding to different algorithms: proximal point, prox linear, which is essentially Gauss-Newton process, or proximal gradient algorithm. Okay, so it turns out that, like I said, if we're next to an active manifold, an active strict saddle, on a neighborhood, this update map is actually a diffeomorphism. So it's smooth. It's a C1 smooth diffeomorphism, despite the problem not itself being smooth. So the function, that thing I'm optimizing, is not smooth, but the update map will be smooth on neighborhood as long as we're next to an active manifold. Moreover, we show that for all three examples, okay, the Jacobian of the update map has an eigenvalue of magnitude bigger than 1. In fact, it has a real eigenvalue that is bigger than 1. Okay, and so this is quite a complicated computation, but this is kind of the crux of the argument. This theorem is to show that if we have a active strict saddle point, okay, then indeed the Jacobian, to translate that into that property, the active strict saddle property is a property of the function. We need to translate that into a property of the Jacobian of the update map for the algorithm. That's kind of where the work is, and that's what we do. So once we prove that, once we make this transition, everything else falls into place by a stable manifold theorem. Okay, so let me just kind of skip this part. Okay, so this is kind of the punchline. So around every active strict saddle point, this iteration mapping is C1, and the Jacobian has a real eigenvalue strictly greater than 1. Okay, that's exactly what I just said. And so as a result, okay, so there's a little bit of a technical detail here that you need what you need to do. There's a little bit of a technical detail in that the update map is not invertible, generally speaking, and you really need it to be invertible. So a little fix is that you shouldn't be looking at the particular algorithm S, but you damp it with an identity. Okay, and so once you damp it with an identity, it becomes a diffeomorphism. The unstableness doesn't change, but once you do that, you can apply the stable manifold theorem, and then you get this theorem which says that if you have a randomly initialized, if you take one of these three algorithms and you randomly initialize that, okay, subject to a tiny amount of damping. So you don't take xt plus 1 really to be sxt, but you damp it a little bit. You average with the identity. It will escape active strict saddle points locally, which essentially means that if you start almost anywhere in the neighborhood, you will immediately you will come out of that neighborhood eventually. So you take a critical point, you run your process. There is a neighborhood, any neighborhood you look at. If you start almost anywhere within that neighborhood, eventually you will come out. And all this local statement becomes global as soon as the update map S is Lipschitz, which is the case for the proximal point and proximal gradient method. So just to reiterate what this means is that for both of these algorithms, prox point and proximal gradient, if you start almost anywhere, the only points you can converge to are local minimi. Let me say it again. For the proximal point, proximal gradient algorithm, if you start almost anywhere, you almost surely will not converge to an active strict saddle. That's the punchline. Okay, for the Prox linear algorithm, this kind of Gauss-Newton update, there's a complication. It turns out it's not known whether the corresponding map, the update map, is a globally Lipschitz, so we couldn't quite make that leap from local to global. But ignoring that case, this essentially settles the question we wanted to address. Okay, so this is the main theorem. Okay, the proximal point, proximal gradient algorithm start almost anywhere in the sense of the big measure. The limit you generate, limiting point, will not be, almost surely, will not be among the active strict saddles. And if all your critical points are either local minimizers or active strict saddles, then you will only converge to local minimizers. Okay. Good. Okay, so this was this paper that I wrote with Damek 2 years ago, I guess. And there was a limitation to this result. Okay, so the limitation is that it applies to these three algorithms. Proximal point, which is not really an implementable algorithm because it's a conceptual algorithm, because the subproblems you need to solve are complicated. Prox linear algorithm, which is an implementable algorithm, but it requires a composite kind of structure. You have to have a composition of a convex function with a smooth map in order to be able to decouple, to linearize the inner map in order to perform the update step. Okay, this is all implementable, but okay, it requires this kind of structure. Prox gradient, which is smooth plus simple proximable, where you linearize the smooth part and leave the proximable term alone. Okay, but all these three algorithms require there is a structured. These are algorithms for structured problems. Okay, you need to be able to do something. These are not black box algorithms. They apply to a particular class of problems. Okay. So this kind of decomposable structure really is key for making these algorithms work. But there is essentially a black box algorithm for minimizing weakly convex functions, and that's the subgradient method. Okay, and so this paper, this work that I just described, does not prove anything about the subgradient method. Okay, so I want to just end. Yeah.
Yeah. Sorry, can I clarify something before you move to this
please.
subgradient method? Right.
Yes, please.
You may mention this. Maybe I missed somehow. So you mentioned this for this active strictly saddle points. You can with high probability, because that's the stable manifold is measure 0. You can avoid. I was wondering how big of this strictly saddle point set compared with all the saddle points, right? So means any point is like a strictly saddle point, or just some of them.
In general, I can cook up very bad functions that have saddle points that are not active strict saddle points, just like the initial example.
Right.
Now the question, okay, is so I provided this theorem which essentially said that any bad critical point is highly unstable because it disappears as soon as you make a small linear perturbation, right? So this is my kind of justification for saying this is a reasonable property. You take any function, any semi-algebraic weakly convex function, do almost any linear perturbation to it, and this property will hold at every non-locally minimizing critical point. Okay, so this is okay, but of course, maybe a more satisfying answer would be to look at concrete problems and ask yourself: Are all critical points either local minimizers or active strict saddles? And this is a very reasonable question to ask.
I see.
For concrete problems, are, for example, arising from statistical, statistical context.
I see. But then when you mention this this proximal gradient or proximal linear algorithms, I'm not sure if you specify what kind of function you apply, or which part I can see you have to use the weakly convex to sort of clarify.
So all of these problems are weakly convex. So so in order to for the proximal point, my assumption is always that f is weakly convex, and so I add a quadratic to it. For the prox linear, it's a composition of a convex function with a smooth function, so it's automatically weakly convex. And for prox gradient, it's smooth plus convex, which is automatically weakly convex.
So in other words, if you have a weakly convex function, so you can characterize how big of this active strictly saddle point, because you mentioned any initial, most of them.
Oh, you're saying, can you characterize kind of the measure of bad initial conditions?
Yes.
That's an interesting question, and it's I don't know the answer to that.
Or the other possible question is like, if we check all the saddle point, how many of them, how big of them they are all active strictly saddle point, or
so that could be very pathological for particular functions. I can make all
even
of them.
for the weakly convex.
Yes. Even for C1.
But then I misunderstood some of the statement. You mentioned for this algorithm, you randomly initialize the point, then generically you can avoid the saddle point, which means
you can avoid active strict saddles.
Oh, you can avoid active. Okay, I see.
Only the active ones. In the same way that for C2 smooth minimization, you're only guaranteed to avoid strict saddles.
Sure.
These are the points where they agree. So it's the same kind of caveat.
I see. But then any kind of objective function, as long as you say I can avoid a strictly saddle point, the statement must be also true, right? Without mentioning whether it's weakly convex or not weakly convex.
Let's just say that again.
For any kind of function, if you say just to avoid the active strictly saddle, because actively strictly saddle, that stable manifold whose measure is just 0. This statement you don't need the weakly convex, or you still need.
Okay, so now things start to get a little bit complicated.
Yeah, maybe we should.
And this is something that I'm going to, if I, oh, okay, I'm kind of out of time. Am I out of time? You actually, Yingyan, how much time do you have left?
10 minutes.
Oh, it's 10 minutes is fine. Okay. So yeah, so then let me maybe sort of comment on that.
I'm sorry about this. Maybe we can talk offline of this if you think it will take you too much time.
Well, no, this is actually what I'm going to talk about now. So let me actually come back to this at the very end. This is exactly what we're going to talk. So once you if you want to talk about algorithms beyond weakly convex setting, well, you shouldn't look at these kinds of algorithms, because these algorithms are only designed for weakly convex problems.
Sure.
Right. So as a result, if we want to go further, we need to talk about a wider class of algorithms. So what's a wider class of algorithm that's applicable beyond weakly convex problems? Subgradient method.
Sure.
And that's what I'm going to talk about now. I'm still going to talk about it in the context of weakly convex problems, and then I will mention what happens outside of this problem class.
Thank you.
At the very end. Okay. So let me just sort of explain what is the subgradient method for weakly convex problems. So now I have to be a little bit careful. So this is a black box algorithm. Does not require any kind of structural assumption how the function is presented to you. Does not require have any kind of decomposable structure. Okay, so if I have, so what is a subgradient? How do we understand the generalized derivatives? Well, the idea is as follows. Well, you know that for convex functions, what is a subgradient? Well, it's subgradient is a vector that defines lower underestimators, lower affine underestimators. So for weakly convex problems, it's the same thing, except you replace the word affine by quadratic. Okay, so the following statement is true. If I have a weakly convex function, then at every point x, there exists a certain element v sub x, a certain vector, so that if I do a linearization, so I use v sub x as the slope, okay, then that's going to minorize my function f by quadratic error. So in other words, if I have a weakly convex function, this is the black, and I have the point x, I can always cook up a lower bounding quadratic that touches my function f at x. And the slope of that function, that quadratic function, of the red function at x, is this vector v sub x. So as a result, we're justified in calling v sub x a subgradient of my function. So subgradient is just the slope of these lower bounding quadratics. Okay, so the subdifferential is just the set of all these v sub x's. And so there's a robust kind of calculus that's very easy to compute these kind of subgradients. For example, if I have a composition of a convex function with a smooth map, these generalized derivatives are just have this kind of simple chain rule. So you just, in order to compute these kinds of subdifferentials, all you have to do is compute subdifferentials of the convex functions. This is completely classical. We know how to compute subdifferential convex functions, and you just hit them with the transpose of the Jacobian of C. Okay, so very robust calculus. In particular, if x bar is a local minimizer, then 0 is in the subdifferential of f at x bar. Okay, good. So here's now an algorithm we're going to be interested in. So what is the subgradient method? The subgradient method is simply this kind of iteration. So given the current point xt, I generate any element from the subdifferential set, any subgradient, and I walk from xt in that direction, and that becomes xt plus 1. So choose an arbitrary, so I just choose an arbitrary element of the subdifferential, walk in that direction from xt, declare that to be xt plus 1, where alpha t is going to be a kind of sublinearly decaying step size parameter. Okay, okay, good. Okay, so let me sort of explain what is fundamentally different about the subgradient method versus the other processes I've defined. Okay, so let's go back to this property of activity. So this is the slide I sort of skipped, but the idea is that for all those algorithms, as soon as I have the activity, so as soon as this manifold is active, as soon as I have a manifold around a critical point that is active, all of the algorithms eventually generate points that only lie on M. Okay, so once I have existence of an active manifold around the critical point, and I run a simple algorithm like proximal gradient, etc. Okay, it's a little bit more complicated for proxilinear, but for proximal gradient, for example, algorithm, if I have an active manifold around the critical point, eventually, once I get close enough to that critical point, all successive iterates will only be on the manifold itself, not of the manifold. And this is this finite identification property, and this is really fundamental. And okay, activity, this sharpness condition, the fact that the gradients are bounded from below outside of M, immediately tells us that eventually, if you when you're sufficiently close to the critical point, all subsequent iterations are actually going to be in M, not close to M, but on the manifold itself. So the manifold captures the entire tail behavior, in principle, of an algorithm that would converge to the point in question. Okay, good. So this is the key property of active manifolds. They capture tails of algorithms. For the subgradient method, this is totally and completely false. Okay, if you apply the subgradient method to the absolute value function, the absolute value function admits the origin 0 as its active manifold, but the subgradient method never hits 0. Okay, so the subgradient method bounces around, and that's the fundamental difficulty. Whereas the proximal gradient method and the proximal point method eventually generate iterates that all lie in M if you're sufficiently close. If you could, then. Yeah, so that's the fundamental distinction. The subgradient method does not have this property. Okay, so, and as a result, it's sort of very hard to understand how to analyze it, because you don't have the smooth reduction, right? Once, like for these fixed point iterations S, once you know that if you're very, very close, S of X is going to be in M, only in M, then you have this reduction in some sense to the smooth setting, because the manifold M is smooth, okay, and all the iterations are on the manifold, even though you start off even though sort of it looks like your update maps are all defined in terms of non-smooth objects, fundamentally in the limit they all become kind of boiled down to being smooth. This totally breaks down for the subgradient method, because the iterates always basically never hit the manifold itself. And so the key idea for how to analyze the subgradient method is an orthogonal decomposition of the trajectory into two bits, the tangent direction and the normal direction. Okay, so there are two kind of ingredients that allow to think about the subgradient process. So these are sort of two technical conditions. They're very intuitive, that allow us to understand avoidance of critical points by the subgradient method. First of all, it should be the case this active manifold has an extra property, which is that the subgradients the negative subgradients points toward the manifold. So in other words, if you start close to the manifold and you walk in the direction of minus a subgradient, you should move towards the manifold. That's the first condition. This is a property one would hope to be true, and actually it is true. Okay, so for weakly convex problems. For non-weakly convex problems, this situation becomes much more complicated, and I can come back to that if there's time. For weakly convex problems, activity implies this. The problem, but then there's an extra condition. The extra condition is we need to sort of think about how do the subgradients relate to the smooth behavior of the function along the manifold. So the function along the manifold is smooth. We're computing subgradients of the manifold. In principle, they could be very distinct. And the sort of property that we would that it turns out to be really useful is if it were the case that in tangent directions to the manifold, the subgradients, sorry, this is a typo, there shouldn't be a V here. The subgradients coincides with the Riemannian gradient of the restriction of F to M up to a linear perturbation, So in other words, in tangent directions, the subgradients of the manifold and the Riemannian gradient of the function along the manifold are off simply by the difference between the point outside xt and the point y on the manifold. Okay, so just on the picture, what this really means is that these two conditions really mean that, okay, if you sort of start off the, so here's a manifold, right? So this is the axis. Of the manifold, like in this picture, you see minus subgradients all point towards the manifold. And the second property tells us that if you look at the subgradient and you project it onto the tangent space of the manifold, then that's actually pretty close to the Riemannian gradient of the function restricted to the manifold. Okay, so we need these two conditions. The first one is essentially automatic if we have weak convexity. The second one is not automatic, and it's an extra condition that is required beyond what we defined as an active strict saddle. However, it again is true for generic weakly convex semi-algebraic problems. So this is yet another kind of condition that is true, that is stable under perturbation. If it fails at an active strict saddle, shake your function a little bit by its linear tilt, it will hold at every critical point. Okay, and so I'm out of time, so let me sort of tell you the punchline. The punchline is that if you look at the subgradient method, but here you don't initialize at random. What you do is you add isotropic noise, a small amount of noise. So you do a subgradient method, but you add a little bit of noise in every iteration that's uniformly distributed. Then almost surely x sub t does not converge to an active strict saddle point. So again, we have this kind of avoidance property, even for the subgradient method. Okay. Right, so as a result, like I mentioned, perturbed subgradient method, this kind of process, subgradient process with isotropic noise, is guaranteed to converge only to local minimizers of generic semi-algebraic weakly convex problems. Yeah, so I'm out of time, but we can maybe talk a little bit later about what happens for outside of the weakly convex setting. I should also mention that there's a concurrent work of Bianchi, Hakem, and Schechtman that has kind of very similar ideas for the subgradient method. So there's a lot of overlap of this last bit of the material with their work. Okay, so let me stop here because I am out of time.
All right, thanks a lot for the talk. A lot of things there.
Thanks.
Yes, because of the time, I suggest to move the discussion offline. So if you want ask questions to our speaker, you can stay here. Otherwise, you are dismissed.